So, continuing with the chemical kinetics only, we will see the dependence of rate of reaction on temperature. The dependence of rate of reaction on temperature. That's very important factor. This one is a lot of things you are going to study upon it. So listen carefully. Now you know that rate of reaction increases with increase in temperature. Rate of reaction. It is estimated that the rate of the reaction becomes double or triple for every 10 degrees centigrade rise in temperature. It is estimated that the rate of reaction becomes either double or it becomes either triple for every 10 degrees centigrade. That means suppose if the reaction is 25 degree and if you increase the reaction by what I can say 25 degree the reaction is taking place, and if you carry out the reaction at 35 degrees centigrade, then you will find the rate becomes either double or triples. The rate is. How it is so? I will explain you in the course of the your teaching. I will explain you that how it is so. Now based upon this, we will be getting a term which is called as temperature coefficient. We can say that. Now what is temperature coefficient? See here. Temperature coefficient. Temperature coefficient is K T plus 10 degree by K T degree centigrade. Of course centigrade, this one is T plus 10 degree centigrade by K 10 degree centigrade. We can say that. That means if the temperature, as I said, is 25 plus 10 35, so K 35 degree centigrade by K 25 degree centigrade, we can say that. So K means your rate constant, you know that. So what I said you, it is estimated that it has been seen that experimentally it has been seen that the rate of reaction become either double or it becomes either triple for every 10 degrees centigrade rise in temperature. When the temperature rises by 10 degree or so, then the rate of the reaction becomes double or triple. How it is, I will come to it, I will tell you later on the reason. Alright, let me finish. Certain terms are there. Now, next is, this is called as temperature coefficient, we can say that. Now, next is, you know that most of the reactions, I told you earlier also this particular thing, that is not carried out at room temperature. Most of the reaction, 99% of the reactions, you know, it is not carried out at room temperature. It is carried out at an elevated temperature. Why? Because at the room temperature, the collision which is taking place, it is not an effective collision. Alright, the room temperature, when two atoms they collide to give rise to a molecule, alright, or two molecules or two reactants they collide to give rise to a product, the collision which is taking place is not an effective collision. Alright, at room temperature in most of the cases, except in case of ionic reaction. Except in ionic reactions, in most of the cases, at room temperature, when the reactant, when the molecules they collide with one another, then the collision is not an effective collision. Now what is effective collision? Effective collision is a collision which gives rise to a product. Alright, because you see that whenever a reaction is taking place, it has to cross two barriers. Whenever any reaction is taking place, it has to cross two barriers. What is that? One is your temperature barrier, another is your energy barrier. Alright, one is a temperature barrier, another is your nothing but orientation barrier. Temperature barrier and orientation barrier. Temperature barrier is also called as energy barrier, and another is your orientation barrier. We can say that. So what is temperature barrier or energy barrier? We can say that. Based upon that only I was speaking to you that whenever a reaction is carried out, it is not carried out at room temperature, it is carried out at an elevated temperature. Why is it so? Now I will explain you this one graphically. Graphically you understand it. This is your energy, alright, and this is your progress of reaction, of a reaction, so to say. This is your energy and this is progress of the reaction. Basically, this much is the energy of the reactant. This much is the energy of the reactant. In most of the cases, the energy of the reactant is this much. Now, this energy is not sufficient to carry out a particular reaction, I said you. It's not sufficient. Why? Because whenever the two reactant molecules they come closer to each other, the old bond is broken. So, for the breaking of this old bond, some energy is required or not? Energy is required for breaking of this old bond. So that much energy which is present in the reactant, that is not sufficient to carry out the reaction. Means it is not sufficient to break this old bond and also the new bond will be formed. It's not sufficient. So hence what will happen? The energy is going to rise. It is going to rise. Alright. That means the potential energy is going to increase. Clear? Now I will explain you with a reaction. You can see. Let us take, I have taken two reactant. One is HH, that is H2, and II, that is I2. We can say that. Now if I write in this way, then I will not be able to explain you. Rather I will be writing in this way. You see that. If I write in this way, then I will be able to explain you properly. Why? That also I will tell you. Because when H and H reacts with I and I, that means H2 reacts with I2. What happens is that this bond has to be broken down. This is the old bond. So it requires energy. Energy has to be absorbed. So what you find is that this much energy which is present at the room temperature, the energy of the reactant, is not sufficient. So energy is going to rise. It is going to rise. Got it? So it is going to rise to a certain level. It is going to rise maximum. Then at that particular, when the energy is rising, what happens? Why energy is rising? Because energy is rising, energy is increasing, energy is absorbed to break this old bond. To break this old bond, the energy is absorbed. The energy is increasing. In this way energy is increasing. It increases to a certain extent. Let us say it increases up to this much. Energy increases. Let us say it increases up to this much. Now when it will reach here, then what is going to happen? It is going to form an activated complex. Means a transition product. An addition product. Means C. That is a bond will develop between H and I. A new bond is going to develop between H and I. A loose bond is going to develop between H and I. Alright, this is called as activated complex or transition state. Now this particular what you can say state is having maximum amount of energy, because this is that state. It is having maximum, see, energy is increasing. It is absorbing energy is increasing. Alright, it is having maximum amount of energy. Now once it reaches the transition state, alright, once it reaches the transition state, it is highly unstable in nature. Highly unstable because energy is maximum. And you know, energy is inversely proportional to stability. Energy is more, stability is less. Fine. So after that, now what will happen is that it has to come to the stable state. So how will it come to the stable state? This old bond will now break and the new bond will develop. Between what? Between H and I. The new bond is going to develop. Between H and I. This loose bond will become now the permanent bond. A new bond will develop. So when the new bond will develop, it will lose energy again. Alright, because what I said, when it is gaining energy, stability is decreasing. When it is gaining energy, why it is gaining energy? To break the old bond. Alright, then after that, when the energy is at the maximum in the transition state, what happens? Then after that, it has to form the product. Why? Because a new bond will develop, because the old bond will break and the new bond will develop between H and I. So when the new bond is going to develop, what I said to you, definitely energy is going to get released. So when the energy is going to get released, the graph is going to come down in this way because energy is releasing. Now the graph can come below or it can come above, depending upon the nature of the reaction. The graph can come. Got it? That means the energy of the product can be either above the energy of the reactant or it can be below the energy of the reactant, depending upon the nature of the reaction. Let us say the energy of the product is above the energy of the reactant. This is your energy of the product. This much is your energy of the product. Let us say EP. So definitely this value, this difference, which is known as delta E or delta H, I can say, which is your change in energy, which is how much? EP minus ER. Alright, EP minus ER. Definitely energy of the product minus energy of the reactant. Last year you studied in thermodynamics, always change in energy, change in enthalpy, whether change in internal energy, whatever it is nothing but energy of the product minus energy of the reactant. Now here energy of the product is more, energy of the reactant is less. You can see very clearly here, energy of the product is more, reactant is less. That is, here it is EP is greater than ER. You can see very clearly. When EP is greater than ER, this answer will come to be as positive. This answer you will get is as positive. That means this is an endothermic reaction. This reaction is endothermic. Alright? Endothermic. This particular, I said, depends upon the nature of the reaction. This is an endothermic reaction. Now suppose the graph comes here. Here it comes. Let us say the graph comes here. You've understood now endothermic? Now let us say the graph comes here. Fine. What is going to happen? Let us see. So, instead of here, now the graph means the energy of the product loses so much of an amount of energy that here the graph comes. Let us see. Here the graph comes. Now this much is your energy of the product. So this difference is your nothing but delta E. Same formula, delta E is equal to EP minus ER. You can see EP is less than ER here. EP is less than ER. So when you will do EP minus ER, the answer is what? Negative. So it is negative means what sort of reaction it is? Exothermic reaction in this way. So it depends upon that how much energy it loses. If the loss in energy is less than that of the reactant, alright, then energy of the product will be less than that of the reactant. So it is an exothermic reaction. If it is more, then it is known as an endothermic reaction. That depends upon the nature of the reaction. Now, here you can see that this is the energy of the reactant. So I have to give an excess amount of energy to carry out the reaction. What is that excess amount of energy called? It is known as activation energy. We can say that. Activation energy, I told you earlier also. This excess amount of energy. And the minimum amount of energy which I am giving, the minimum amount of energy, this is a minimum I have to give it. Because this much is not sufficient. I have to reach to this level. Then only the reaction will be carried out. Because this much amount of energy the reactant is absorbing. So this is the minimum energy I am giving it. Minimum. This much. From here to here. What is that called? Threshold energy. So the minimum amount of energy which is required by the reactant molecules to carry out a reaction is called as threshold energy. And the excess amount of energy, because this is the energy of the reactant, so I have to give something excess. So the excess amount of energy which is required by the reactant molecules to reach to the threshold level, mind it here, to reach to the threshold level is known as what? Activation energy. Then what I get the formula from here? ETH is equal to, that is nothing but EA, energy of the activation energy plus energy of the reactant, plus ER. Or activation energy is nothing but threshold energy minus energy of the reactant. Activation energy, we can say that. Definitely activation energy is threshold energy minus energy of the reactant. In this way, we come to know what is activation energy, what is threshold energy, what is temperature coefficient. Got it? So this is nothing but is your energy barrier which I was talking to you. So every reactant molecule has to cross this energy barrier. Every reactant molecule. That depends upon the nature of the reactant, we can say that. In certain cases, this energy barrier is less. In certain cases, the energy barrier is more. Every reactant molecule, because it will absorb the energy. Then only the old bond will be broken and the new bond will be formed. But one more thing I will tell you. Now this this particular position I said, that transition state or activated complex. Now here only it is decided, listen carefully, here only it is decided whether the reaction should go in forward direction or it should go in backward direction. How? Because if by going in the forward direction, if the energy is lowered, then it will go in the forward direction. Because always the reaction will take place in that particular direction in which the energy is lowered. Why? Because why a reaction is taking place? To attain stability. So if by going in the forward direction, if it is attaining stability, then the reaction will go in forward direction. If by going in the backward direction it will attain stability, alright, then it will go in the backward direction. So this points decide, the activated complex or the transition state decides whether the reaction should go in the forward or whether the reaction should go in the backward direction. Alright, so hence the reversibility of the reaction also is being decided, whether the reaction is being reversible or irreversible, the reaction also is decided with the activated complex. Very simple it is. Because always the reaction will take place in that particular direction only where there is lowering of energy. Lowering, where the energy lowering is being taking place. In whichever direction it will go and the energy lowering is taking place, the reaction will move in that particular direction. That is a natural. This is simple science, we can say that. Alright, simple science it is. So if the reaction is carried out in the forward direction, by which lowering of energy is going to take place, it will go in the forward direction. And by carrying out in the backward direction, the energy lowering is taking place, then it will go in the backward direction. Alright, in that case, you might be wondering how it is possible. In that case, this becomes your reactant and this becomes your product. This becomes your reactant and this becomes your product, we can say that. Because you will draw a graph, imaginary line, in that particular case you will be drawing it and you will be finding the, what you can say, the reactant and the product. So hence, you will see that. So how you draw the imaginary line? Let us say the graph goes in the backward direction, it goes here. So hence you draw up a straight line from here. Alright, you drop a straight line from here, you drop a straight line. So you get, this is nothing but the energy of the product, you get it, this one. So hence you draw imaginary line from here and we find it out. In imaginary line, let me tell you that. In imaginary, because this is not taking place, na? Taking place is this, backward. Are you getting me? Suppose the reaction goes in the backward direction. How will you know? What I said you? This becomes a reactant and this becomes a product. Na? Backward means this is the reactant and this is the product. So in that case, what do you need to draw? Suppose the reaction comes and stops here. Or here it comes and stops, let us say. So in that case, what are you supposed to draw? A straight line. Or you will say, suppose the reaction comes here and stops. You will draw a straight line. And from there, you will draw a dotted line from here. An imaginary. So hence, this will give the reactant and this will give the product. In this way, we will find it out. That's it. Clear? So that is called as the activation energy in the backward direction. And this is known as activation energy in the forward direction. I hope you understood this particular thing. Thank you.